In this video, we're going to talk about the first part of what is needed to be able to run a multivariate GWAS. So this is step 4, where step 1 was MUNGE, step 2 was LDSC, step 3 is user models, so estimating the structural equation model at the genome-wide level. And now here we're running the sumstats function, again, to be able to estimate that multivariate GWAS. Sumstats, I would say, tends to be the function that causes the most confusion, and that's in part because you need to know slightly more information than you had when you ran the MUNGE step, specifically related to how the effect columns are scaled. But going specifically through the arguments themselves, the first one is files. So this is the name of the summary statistics files, not the MUNGed files. So here you're going to be providing the same files that you gave to the MUNGE function, so the GWAS data prior to running MUNGE, and they should be listed in the same order that was used for the LDSC function in step 2. This is really important because the ordering is used to line up the estimates from the GWAS with the LDSC estimates. So if you don't put them in the right order, then you're going to have the wrong SNP effects going with the wrong traits. The second argument is a different reference file. So this is a full 1,000 genomes phase 3 reference file that includes closer to 10 million SNPs. And that's also available on the GitHub and can be downloaded at this link. So this reference file is used to align to the same effect allele, and it's also used to calculate the SNP variance across traits, which is used to fill in that LDSC matrix in a way that I'll describe in a few slides. So unlike with MUNGE, you do expect to end up with a much larger set of SNPs. Here we are concerned with genomic coverage and how many SNPs are left in the data sets. It is going to use listwise deletion across the traits. So if you have one trait that is much older than the other GWAS, odds are you have worse coverage, you have less SNPs. And so if for one trait it's dropping your total SNP list in half, you'd really want to consider how important that trait is within the broader constellation of traits that you're modeling. So the third argument is the trait names. This is just how the traits are going to be named in the output in the columns. And then these last 4 arguments are the ones that tend to cause confusion. So the first one of those here, argument number 4, is standard error.logit. So this is whether or not the standard errors are on a logistic scale. This is guaranteed to be false for a continuous trait. This will only be relevant for binary traits. This should be a vector that lists true or false for all traits. If you have all continuous traits, you could just not specify this argument at all. It will automatically fill in false for everything. But if you have all binary traits or a combination of binary and continuous, you're going to want to provide a full set of arguments with the same length as you have for the files argument up here. A word of caution that you really do want to look at the README files for your binary traits to determine whether or not the standard error is on a logistic scale. It's sometimes done that you have a effect column that is an odds ratio, but a standard error column that is for a logistic beta. So there's this actual kind of purposeful misalignment between the effect column and the standard errors. There's different reasons for that, but all that to say that you might be surprised that you do in fact have logistic standard errors even when that effect column is listed as an odds ratio. The fifth argument is only going to be relevant when you have continuous traits, and this is used to specify whether or not an observed least squares estimator was used where a continuous outcome was analyzed using a linear estimator. So if you have, for example, a standard GWAS of height, BMI, cognition as a continuous measure, then you're going to be setting true for this argument. The sixth argument here is linprob, which stands for linear probability model, which is what you would use when you only have z-statistics for either a binary or continuous outcome. So there's not a beta column or an odds ratio column. Or if you have a dichotomous outcome that was analyzed using a linear estimator. This is actually a somewhat common practice because linear estimators are much more efficient than logistic estimators, and the p-values that you get are perhaps surprisingly similar, so that for computationally efficient reasons, people will use an OLS estimator purposefully with a binary outcome. That's maybe becoming less common practice as the estimators are getting more and more efficient. But for now, there are GWAS out there where you might have a binary outcome that was analyzed using OLS. And in that case, you need to be setting linprob to true. The seventh argument you only need when you have a continuous trait or when linprob is set to true. It's a user-provided sample size, and if it's a linear probability model for a binary trait, this, like in MUN, should be the sum of effective sample sizes. That might be a lot to keep in your working memory. There's a flowchart on the GitHub to help you figure out the specific set of arguments you need for each trait for sumstats. Again, 4, 5, and 6 are going to be vectors of trues and falses, and which ones you're setting to true and false are going to require looking at the README, understanding what kind of estimator was used, linear or logistic, and understanding the scale of the outcome as well as the standard errors, which sometimes may surprise you in that they can be logistic even if it's an odds ratio in the effect column. So here's an example actually of where the linear probability model needs to get used, where in the alcohol GWAS data, you have chromosome, SNP, A1, A2, but instead of an effect column, you just have the Z statistic. And so here we're going to set linprob to true, but you're going to see in the code in a second that we're still going to set NA for sample size, because this weight column you would see in the README is actually the sum of effective sample size from the Riccapilli pipeline for the PGC. So we don't need to separately provide value for that argument because we have the SNP specific values here. So actually, let's go to the code here. So a really important note that during the workshop and in this video, I've subset the data to just chromosome 4, only because sumstats can take a few minutes longer, so just for the purposes of keeping things timely, I've only got chromosome 4 here, but in practice, you are definitely going to use all chromosomes at once. This is not something that I would split across chromosomes in the way that sometimes people set up their GWAS to run on computing clusters. I'm just subsetting to chromosome 4 so that this runs and we can quickly look at how the code is working. So here I've got my GWAS files, that reference file, which again, just for the purposes of this exercise, has been subset to chromosome 4. The trait names, again, remember these are in the order that we had for LDSC of alcohol, PTSD, MDD, and last anxiety. Standard error.logistics, so I know from the README files and from looking at the data that PTSD, MDD, and anxiety do have logistic standard errors, whereas alcohol, as we just saw in the slides, only has a Z statistic. So I'm setting 1 false and 3 trues. And then linear probability, I'm only setting true for alcohol. And as I mentioned, I would typically put a value in this first spot for alcohol with the sum of effective sample size, except that in this case, alcohol has that weight column, which reflects the sum of effective sample size directly in the data. And we also don't have any continuous traits, so here I just list all of the ends as blank because it's not relevant. And then finally, we put it all together. And we run. And what you can see here is this ran super quickly because it was just on chromosome 4. Only 1,000 SNPs are left, but in the end, you should expect to see on the scale of 1 to maybe 5 million SNPs after listwise deletion across all of the included GWAS. Just like with Munge, there's going to be a log file created. So if we go to our folder that we're running from, here we have the log file. And at the end, again, it's only got 1,000 SNPs here for the purposes of that practical, but just going back to the slides, here I've got the sumstats.log file when I ran the full set of GWAS data. And there, it didn't take that long, only 9 minutes, and we've got 5,300,000 SNPs, more or less, that are left after the listwise deletion across those 4 traits. So now that we've run sumstats, we can go on to the final step, which is integrating the SNP data to then estimate the model, including the effects of individual genetic variants. So in this case, we're going to estimate the effect of a SNP on that internalizing latent factor defined by those 4 traits.